recording and stop talking about management. That was like the start of every video I had last semester. I was really ticked off. Okay, so we got this h of 0, and I came up with this equation, and I just got this question here. And this is number 11. So maybe I can recreate that equation and get it from here. So when I did h of 0, what I got was 10 over 2 times 10 equals 5 over 2 plus c over 10. And I just really quickly solved this on my calculator. And what I was really doing is I was taking, well, 10 over 10, the 10 cancels out. So I have 1/2. I move the 5/2 over, so it becomes negative. And then I would multiply by 10, and that would equal c. And I did all that punching numbers on my calculator, but and that came up with c equals -20. And that's where I think we were at. For h of 1, yeah, I got my cheat sheet in front of me. 10 over 3 times 17 equals 5/3 plus 13 minus 20 over whatchamacallit, 17. Oh, and that wasn't a 13, that was this is a B. I can't read my own handwriting. And again, I could move the 5/3 over to the other side, multiply by 17, and then add 20, and I would come up with B. They're really messy, one equations and one unknown, but that's really all it is. B is -5. Okay, so we have a value of A. What the heck was A? A was 5. We got that before with using residues. We got B is -5, and we've got C is 10. Where would we go from here? This is just going to be an exponential, 5e to the -2t. This one right here, I've got to put it in the form of those damp sines and cosines, just like we did on the last problem. C is -20. Yes, it is. That's what it says, right? Somewhere right about here. Okay. Oh, you're right. C is -20. Yeah, you're right. Okay, so we could go through and do all that. We've got A, B, and C. And we can go through and do linear combinations. We've already done one of those. Now, a lot of rigmarole in here. How many more of these do I have? Okay. We've got this function right here. I want you to understand the procedure more than anything else. I'll help you get started on the homework. First step, we write this. We've got this h of s. We want to find h of t. We write it as a partial fraction expansion. We find A, B, and C using some combination of residues and substitution. Once we find A, B, and C, we take the inverse Laplace transform. And this one turned out to be easy because B was -4. Yeah, so it's a cosine. It's a damped cosine. So we just had to get it in this form, s plus a over s plus a squared plus omega squared. And that may involve some completing the square. Is everybody okay? Or are you just like, I don't want to do this anymore? Is this like, or is it just a review of Calc 2? Fortunately, you've taken that recently. I took that, I can tell you what year it was. It was 1983. But then I got the extra pain of my kids going through high school. And I for some reason, or I thought it'd be fun to homeschool my son. So I got to teach him Calc 2. Yet he was stubborner than I was. Okay, why we do this S domain analysis. Controls engineers, and we do have a controls engineering elective now, which is an amazing thing that hasn't been around for a couple of years. They're people who want to maintain stable systems. If you're working for the power company, you want to maintain a very stable system. If you're doing any kind of power conversion, you want to maintain stability. If you're doing control systems, like there's a lot of control systems inside of vehicles. There's a lot of controls, like the air conditioning system in here, where you really want to maintain like a stable temperature, a stable pressure in a system or something like that. It requires this controls theory. And it's kind of like one of the kind of keystone classes that we've been missing for a while, but we've got it now. Okay. Controls engineers, they do this they plot complex poles and zeros, and they plot the poles and zeros on a sigma plus j omega plane. Notice here, there is no graph whatsoever if sigma is greater than 0. Because what happens if sigma is greater than 0? You have e to the sigma t. You've got something that does not maintain stability whatsoever. It goes to infinity. So they just ignore it like it doesn't work. It doesn't happen. This is all unstable. If you get poles and zeros inside these unstable regions, you just fix your system. Okay. If I have, this is called right here a pole at the, it's a 0 because it's a 0. This is a 0 at the origin. And it's literally at the origin of this axis system. If I get poles and zeros there, they're marginally stable. I can handle one of them. If I get 2 of them there, my system tends to go unstable. And I talk about this a lot in 325, which I don't teach anymore. But so right here, this s squared term is going to give me 2 zeros at the origin, because those are places where the function goes to 0. If I factor my denominator, I have something that looks like a complex conjugate pair of poles. They are at 1, it says 1 plus 2j, which means s would go to 0 at -1 minus 2j. So I go over here and I plot -1 minus 2j, and I get an x, and an x indicates that it's a pole. And I get a pair of these things. And poles are places where my function is going to go to infinity. Now you can actually take this with, I think these were done in Mathematica, believe it or not. You can take, not MATLAB, you can take these and graph these on a 3D plane. So if you think of this as being the 2 dimensions is what you're seeing, the 3rd dimension is the magnitude of the function. So right at the origin, the magnitude of the transfer function should go to 0, and right at these 2 poles, it should go to infinity or be spiky. So these are the Mathematica versions of the same thing. You can see as you approach the poles, you get these peaks. And I'm not going to talk about you can get more of this in controls theory. I believe Dr. S is going to teach that class, which would be amazing. He's good. Ex-military, he's nothing like me. If I look at it on the other axis, it looks like the Motorola bat wings, but you can see that if I zeroed in this resolution here, this would keep, if I did more points in between there, the points would keep going up and eventually reach infinity. So that's my talk on control. Oh, one more thing. Sorry. If you plot, and this is just a preview. If you plot the magnitude of this function, just like we did magnitude and phase back in 188, versus frequency, and you do this on a linear scale, you get something that is not really all that, it's not as useful. And it was really hard to plot these back in the day. There was a guy at Bell Labs, of course. Oh, he's a slide rule genius. And he figured out, if I take this same plot and plot the log of the frequency on the frequency of the linear frequency on a log scale, the logarithm using decibels on a linear scale on this axis, pretty much most of these transfer functions come out to be things that you can approximate by straight line segments. And they're really easy to draw once you get the hang of it. And I'm sorry about what's coming next, but we're going to do this. This is going to be the next week of class, and it's this thing called Bode plots. People hate them when they get to 280, but they are amazingly useful because your test equipment will give you information out on plots that look like this. You can manipulate them in MATLAB. You can do all kinds of things at it. Drawing them by hand is not fun, but you have to do it once. And this is your once. Okay, and we'll try to get through this, but I'm done. And it's Wednesday night, so I get pizza night. Which doesn't involve pizza anymore because my friends won't go out to the restaurant and eat pizza, so we just have a potluck at home. Let's see, who am I missing off the roll? Yell at me. Lauren. Jordan, I saw you at some point. It's gonna Peter Schoen and Ibrahim. Ibrahim King. Okay, somebody's chatting. I will look at that. Sounds fun, yeah. I'm sorry. And then you'll wonder why I like semiconductor physics so much. We'll get there. Don't save. Stop share.